And let's do another cosmology segment. Now, we like to talk cosmology regularly because it is a perfect example of a science that it is in the process of being rewritten. And so we talk about it all the time, as there are all kinds of articles coming out and all kinds of interesting facts. Let's talk cosmic rays. Cosmic rays are typically particles coming from outside the solar system, from different stars and indeed different galaxies. When cosmic rays strike things, they create secondary particle showers. So let's just say that this right here, let's say this is a hydrogen nucleus, right? Hydrogen nuclei are the most common type of cosmic rays, as well as the most common component of the solar wind, making up about 90% of the solar wind. When a cosmic ray strikes the Earth's atmosphere, it's going to make it through until it starts striking things. And when it starts striking things, it'll probably steal an electron, and then it's going to create an ion from that stolen electron, and that particle is going to want to do a chemical reaction with something to either give up another electron or take an electron back. Meanwhile, you have what we call an ionization pathway. And this process, as protons traveling at nearly the speed of light are decelerated as they hit the atmosphere, these cause clouds to form. So if you want to read about it, there's an article on space.com that we've actually featured here. Space.com, What Are Cosmic Rays? That's from 2018. Perhaps have a read on that. Cosmic rays are super important in climate, and they're not yet figured into climate models as far as I know, in that in 1996 the Svensmarks discovered that cosmic rays cause clouds to form. Clouds tend to form on these ionization pathways, and you can find all over the internet information about the way water reacts. So if water is exposed to a positive anode, water is pushed away from the positive anode. And if water is exposed to a negative anode, with current, of course, in both instances, water is pulled toward the negative anode. So as you could imagine, that would affect the Earth's atmosphere, and indeed cosmic rays do. They have the ability to make the Earth cloudy over an extended period of time. So let's look at some cosmic ray monitors. We do this about twice a week. Here is the neutron monitor at Apatity, and you can see a downward trend here over the past 30 days at Apatity. And at Barentsburg, also a downward trend there over the past 30 days. Let's go someplace farther south. How about Athens, Greece? Did I fail to show that? I failed to show it, folks. I apologize. Back to Apatity and Barentsburg. So there's Apatity. You can see that 30-day downward trend. And here is Barentsburg. There's the 30-day downward trend at Barentsburg. Next, Athens, Greece. Let's try this again. There we go. There's Athens, Greece over the past 30 days. Slight downtick at Athens as well. So despite this very weak level of solar activity, cosmic rays seem to still be going down. Mexico City's flat here over the past 30 days and down over the past 2 weeks. And next we'll go to Oulu, Finland, and 2 Antarctican monitors. There's Oulu. Downtick at Oulu over the past 30. Here's DOMB Antarctica. A downtick at DOMB Antarctica over the past 30 days. And there's DOMC Antarctica, a downtick there as well. Now, I talked about Twitter. The only place I put these links were on the Twitter feed. You can find them on the Thunderbolts.info forum as well. Mr. Bagashov created like his cliff notes for Anthony Peratt's Physics of the Plasma Universe, a book he does not like, as well as Alphane's Cosmic Plasma from 1981, a book that he does like. If you'd like to read those books without entirely reading those books, perhaps check out Eugene's synopses here. Thanks to Eugene. Hit me up, we'll make that coronal holes video at your leisure. Now let's pick a random object here. we're going to use our random quantum number generator here. Anu.Korn. We're going to pick a random number between 1 and 1031, which will coincide to an object at Neil Garrel's Swift Bat X-ray Observatory. Today's random number is 899. Let's see what it lines up with. 899 happens to be 1ES1959 plus 650, a BL Lacertae object, a type of quasar, which has a broad band emission spectra. So BL Lacertae objects, instead of only showing up in one frequency, they show up across the entire electromagnetic spectrum. And 1ES1959 plus 650 is a consistent X-ray source, as you can see here. No apparent cycle with it. And there's the last 30 days of that. Let's see if we can get a glimpse of it on the SIMBAD. And there is that BL Lacertae object, a type of wide emission spectral band galaxy. So it's a type of active galactic nucleus where you're looking right down the poloidal field. And what I mean by that is if this was a spiral galaxy, there's a field coming out of the galactic core of that galaxy. And depending on your location, you may be looking right down the pole. If you're looking at it more like kind of from the side like this, that field is going to come out in this sort of direction. And if you're inside that jet, the galaxy will be a quasar, a quasi-stellar object, as they're still called. We now know what they are. It's just a matter of perspective. So there's a view of that 1ES 1959 plus 1650. Let's look at it on Aladdin Light and see if we can see it in a couple different spectral bands. Here it is on the 2MASS. That is infrared light. And we'll see if we can see it on the XMM. There it is on the multi-mirror X-ray project, the XMM Newton. And it doesn't show up on Chandra. How about the Swift Bat Flux? It does show up as a bright spot there on the Swift Bat Flux. And we'll go back to the 2MASS here. So we'll zoom way in. And there's Quasar 1959 plus 650. Today's featured object, 1ES 1959 plus 650, the featured object on today's Cosmology segment. Let's get back to current data. A tiny solar flare occurred as we did the show.